Welcome to an exploration of iOS architecture. In this presentation, we will delve into the design principles and security features that make up the iOS operating system. iOS employs a layered architecture, a modular design that uses distinct layers of abstraction. Each layer provides specific services to the layers above it, ensuring security through layer isolation and restricting hardware access to the lower layers. The layers from top to bottom are the application layer, frameworks layer, core operating system layer, and the hardware layer. The iOS is built upon several core design principles. First, security is integrated into the very foundation of iOS with multiple layers of protection, including a secure boot chain, app sandboxing, data encryption, and secure hardware elements. Second, performance optimization. iOS maximizes device capabilities while minimizing resource usage through efficient memory management, power-saving techniques, hardware-software integration, and an optimized rendering pipeline. Third, modular architecture. The system has a clear separation of concerns, with distinct functional layers, well-defined interfaces, encapsulated components, and controlled dependencies. App Sandboxing is a crucial security feature in iOS. Each app is isolated with its own private file storage area inaccessible to other apps. Apps can only access system resources through controlled application programming interfaces. User consent is explicitly required to access sensitive data or hardware. The system prevents apps from executing malicious code or accessing memory of other apps, providing runtime protection. The Secure Enclave is a hardware-based security component. It is a physically separate processor with dedicated secure boot and memory. It handles cryptographic operations, key management, and secure authentication. It securely processes face identification and touch identification data without exposing it to the main central processing unit. It is designed to resist physical and software attacks on sensitive data. iOS offers robust data protection mechanisms, including file protection. To set a file's protection level, define the file's location and write data to it, specifying options like complete file protection, which encrypts files and makes them inaccessible when the device is locked. Other protection levels include complete unless open, complete until first user authentication, and none. iOS also employs hardware-based encryption, using the device's dedicated advanced encryption standard engine for efficient encryption and decryption, as well as per file keys, where each file is encrypted with its own unique key for enhanced security. The secure boot chain ensures that only trusted software is loaded during startup. First, the boot read-only memory, which is immutable code, verifies the low-level bootloader. Second, the low-level bootloader verifies the signature of iBoot. Third, iBoot verifies the signature of the iOS kernel. Fourth, the kernel verifies all boot time processes. Finally, iOS is ready, a secure system ready for operation. Each step involves cryptographic verification of the next component before execution, forming a chain of trust. If any verification fails, the boot process halts immediately. The boot read-only memory code is unchangeable and embedded in silicon, providing a hardware root of trust. The boot chain also prevents installation of older, vulnerable iOS versions, offering downgrade protection. iOS incorporates several advanced security features. Keychain services provide a secure storage mechanism for sensitive data like passwords, keys, and certificates, offering hardware-backed encryption, access control based on app identity, and biometric protection options. Biometric authentication enables secure identity verification using physical characteristics such as face identification, which uses 3D facial recognition, and touch identification, which uses fingerprint scanning. Biometric data never leaves the Secure Enclave. App Transport Security enforces secure connections between apps and web services, requiring Hypertext Transfer Protocol secure connections, enforcing Transport Layer Security version 1.2 or higher, and ensuring forward secrecy for connections. App code signing ensures apps come from approved sources and haven't been tampered with, verifying developer identification, performing runtime verification of code integrity, and involving an App Store review process. In summary, the key aspects of iOS architecture are architectural design, security foundations, and security features. Architectural design involves a layered architecture with clear separation, modular components with defined interfaces, hardware-software integration, and performance optimization. Security foundations include a secure boot chain, App Sandboxing, the Secure Enclave, and data protection. Security features consist of biometric authentication, keychain services, app transport security, and code signing. In conclusion, the iOS architecture shows how security can be integrated at every level of an operating system. From hardware foundations to application frameworks, the design principles prioritize user privacy and system integrity while maintaining performance and usability. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.